He's from Canada, I thought, too. Maybe the
Oh,
Canadian
so he's
side
from
of
like
it.
Native things.
Yeah, and then
Because he has that like French Canadian accent.
he also was like the world's greatest breakfast lettering teacher because he would go, how do you love recognition? Yes, write one, send it to me. Said that immediately.
That's hilarious. That's sick.
Okay. Questions about anything? Homework 5, homework 6, yeah.
I was just gonna say thank you for the extension on homework 5. I think I, and probably most of us, very much appreciated it. I needed it. Thank you.
Uh, Given deadline of homework 6, but sure, and homework 7 that will be appearing also, but fine with me to have an extension. Uh, which questions uh, do we do you want to talk it over? Do you want to, like, we can uh, about if you need help, hints, anything? Yeah.
For the one where we're trying to have a bounding box with the triangles, and we want to get it down to O of log to the fourth of n. Do you remember that one?
Yeah,
Do you have any hints for us on how to like remove the two dimensions from the tree?
you just said it. You, uh, triangle has 6 points, so I need log to the 6. But give me a condition that a rectangle will contain a triangle. You just said it. It needs to contain something of the triangle. That mm,
Right, the three vertices, and then
yes, but you can. But the query is an axis parallel rectangle. And if it contains a triangle, then it contains a bounding box of the triangle. That's it. That's, yeah. Yeah, that's what. Yeah. Yeah. So yeah, that's so sure. Other things that gives you hard time. I said the proof of the union of the tilted squares. There are a bit case analysis. It's not hard, but you want to you want to compute the union of the axis aligned squares, and shows that there are a linear number of vertices. Then you want to compute the union of the tilted squares. And then you put their union together, and you want to say every new vertex that I generate, I can walk away from this vertex and hit one of the vertices of this union that I just had. And it sounds a bit abstract. You want to say, here is a, I'll just give you one of the cases. Here is one tilted square, and we stop. One square, and here are two tilted squares. I know how many vertices the union of the red guys have, that there is only linear number of them. I know how many vertices the black guys have, just linear number of them. Vertices might be a vertex as so, a corner of a square, or the intersection, the union of two such square like so. That's another type of vertices, but you know that they are only linear number, and we saw a few proof of it. One was by charging scheme. We said from such a vertex I'll go inside, and because they are all unit square, I will not exit from this square before I hit the corner of this one. So this vertex is uniquely charged. That was one proof. Another proof is by you saying that unit square are, help? Pseudodisks. So they don't, but these and these are not pseudodisks, so I need a slightly different argument. So you want to say, here is such a vertex, and if I'll just walk towards the end of the square, so maybe I'll hit the corner of this red square, maybe I'll hit a vertex, but, and there is even a chance that I'll exit, and that's the embarrassing cases. There is a chance that I'll exit this square, but it will not happen frequently. It can happen once per square. So it's a bit careful and a bit tedious case to prove that there are very few vertices that you don't have anybody to charge. What do I mean to charge? What goes wrong when I'm trying to apply it for rectangles is, union of rectangles in general can have n square complexity. And if I'll try to say, here is where I put my money in, $2 in the corner of this rectangle, and from this vertex, I'll try to charge this one. If you understand me, great. If not, I said it's a bit higher for this course. I'll walk from this vertex trying to reach a vertex that I can charge to. So if I'll put $2 on every vertex that stores money, and then I'll charge it only from two other vertices, then I don't have more than 2n many vertices. So what's go wrong in a rectangle? Here is a vertex of the union. I'll keep walking. So V1 wants to charge U, but V2 over here also to charge U, and I can place n such guys. And we know that the union of rectangles have n square complexity. And why should you care about all of it? Because if your robot is strange and you can have some free cells, free face of the robot, if your objects overlap each other. So maybe it's a bit interesting in terms of robotics. That's where the source of all these problems are, from past planning of robotics. But anyhow, that's about the union. So you can solve this problem if you want, and I'll be impressed. Or you can leave it on and continue further, and I'll take very few points. But the other questions were more humane. So anything about the other questions?
For the question about proving the complexity of the unbound faces.
Yeah.
How should we approach that proof? I thought maybe a proof by induction might be a good idea, and then I made almost no progress.
Well, you have the zone theorem. But the zone theorem asks for a line. If I look at a line in an arrangement and ask what's the complexity of all these faces, it will be linear. Now, I cannot hit all the unbounded face with one line, but I can hit all of them with two or so many lines. That's it. Yeah, take the whole arrangement, put two lines on the sides. So every face either meets a line way to the left or a line way to the right. So that's all it takes. So it's whatever was the zone theorem for one line, now it's twice, because it's one of the two lines, and maybe I double count. And I want to speak about linear programming and an algorithm that was a nice breakthrough, because it was a hot topic for many years, to see how fast can I do linear programming in lower dimensions. But before that, just a bit probability to remind you stuff that I assume all of you knows. Here is a square of size 1 by 1. Here is a shape A, and I can ask, I drop an arrow, I shoot at it, I pick a point at random, and I ask what is the probability that I hit A. And the probability is, of course, the area of A divided by the area of the outside square. I told you that I hit the square for sure. What the probability is that I hit A itself, and it's just the probability of A divided by 1. And now I can define a random variable, which is probably you played this before. If you didn't play with random variable before, then think about a random variable. X would be a random variables, which I found as unbelievably confusing terminology, thinking about it, calling it a variable. It was somehow a function that takes something that happens when I do my trial and connect a numerical value to it. And the random variables that you'll see coming up are all Booleans, 0 or 1. So X would be a random variable, which will just say X equal 1 is just a flag that said if I hit A, and X equal 0 if I missed A. My arrow hits some point outside A. Okay, so if you don't like the term random variable, just think about it as a flag on or off, depending on the result of your experiment. And then you can ask, what is the expected value? Expected value of X, average value, I drop billions points. Here, every point is uniformly at random. What would be the average number that I'll get? So expected value says check all the values that X can get, and for each one multiply by the probability that it happens. But the value that, normally the formula of E of X is just sum up over all the I starts from minus infinity to infinity of X of I times probability that X equal I. That's just the definition of expected value if X is only integer. If X was a float, I should have used an integral over here. But don't panic immediately, because X here is just a Boolean value. So the probability that X equals 3 is absolutely 0. X is my flag, then I can get only 0 or 1. So probability that X equals 17 is completely 0. Probability that X equals 0 well, I can compute it, but I don't care because there is an I over here. I multiply it by what is the value of I. So if I equals 0, then I don't care what's written here. The only case that this expression is not 0 is only if I equal 1, because x cannot get anything else besides 0 or 1. So all I'm left with here is that the expected value over here is nothing but the probability that x equals 1. So far, so good. Just the average value of x is just the area of x, right? Makes sense. I throw billion points here. What's the probability that, what is the expected value of x is 1? Or 0 is just a portion of points from all my sample, my billion points. What is a portion of the area of A divided by the portion of the whole square, which is 1? Let's define yet another shape, B. And I can define y as another random variable. Y would be a random var as well. And what is this random variable? Y equals 1 if and only if we hit B, the wedge shape. Okay. And there is a chance that I hit both A and B. There is a chance that I hit only A and not B. I can ask now what is the expected value of y, which is, once again, just the probability that of hitting y, which is what? It's just a probability because of the same reasons. If it was true for x, y and b behave the same way. Just probability of y is just a portion of the area of y. But now I can define a new random variable, which now has 3 values, 0, 1, or 2, which would be x plus y. And this guy has 3 possible values. It can be 0, if both are 0. It can be 1, if only 1. Or it can be 2, because each one of x could be either 0 or 1. First flag, y can be either 0 or 1. And I can ask what is the expected value of this new random variable, x plus y, which is the probability of something. What's the I need to sum up now the probability that it's 0, and that x plus y is 0. What's the probability that x plus y is 1? What's the probability that x plus y is 2? And so on. But here I'm going to use simply to describe, but a very strong property. Right? I placed A and B such that if I hit A, then I am completely outside B, and vice versa. They are completely disjoint. So these now they are conditioned in each other. If you hit A, you definitely don't hit B, and vice versa. Or I can draw them so they are the same shape. If you hit A, then with probability 1, you hit B, and vice versa. Or they can be conditioned in all kinds of ways. The beauty of this expression is that the expected value of the sum is just E of x plus E of y. E of x plus E of y. And I don't care at all how x and y refers to each other. Maybe they are independent, if you know from probability what is independent. If you take, say, 380, that makes sense. Maybe they are not independent. Maybe they are mutually excluded. I don't care. This is true no matter what. And similarly, if I'll have more random variables, x1, x2, xn, then the expected value of the sum of the xi is just the sum of the expected value of the xi's. Sum of expectation. And I can define yet another random variable that would be 3 times x. So what is 3 times x? I through the arrow. If I hit A, then this new random variable will give me 3, because x is 1, so 3 times 1. Otherwise, it's 0. So what is E of 3x? It's 3E of x. So linearity of expectation also means that if you take such a random variable and multiply by a constant, it's the constant multiplies the expectation. Okay, it's beautiful proof, but I'm not going to show it right now. Why the expectation of the sum is the sum of the expectation. It's actually not that obvious and quite surprising, but very strong. Okay, put it all in the back burner. We had a linear programming problem. We have a set of values, alpha 1 dot 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 alpha n, beta 1 dot 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 beta n. I am trying to find the maximum x such that the maximum value of x such that x is smaller than all the betas, but x is larger than all the alphas. And we had a linear time algorithm for it, which was very trivial. Find the maximum out of all the alphas, find the minimum of all the betas, and if there is any portion between the alphas and the betas, all the betas, or the maximum of the alpha, the minimum of the beta, then the maximum value in this interval is what you're returning. That is just this point. And it can also be that you realize that there is no point at all because the maximum of the beta is larger than the minimum of the alphas. Now I want to show you one-dimensional linear programming, but rotated. And I'll use these notations later. So it's called one-dimensional, 1D, linear programming of a line L. That is, I'm looking for a solution that is a point. It's a two-dimensional point, but I'm only selecting points from points along the line L. And in addition, I want to give you a set of half-planes. So in this case, h1 dot 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 hn are half-planes. So h3 are all the points that are above the line. Remember, the little fair over here means all the points on the upper side of the half-planes h3, all the points that are below the half-plane, the line that defines h5. And in addition, I'm only looking for the points that are on the line L. And I want to convince you that it is as simple as solving the one-dimensional LP that we had one slide ago, except that then it was on the x-axis, and now the x-axis is shifted, so it coincides with L. But it's an important point, so let's make sure that first everybody understands what is the input of the problem. Input of the problem is I give you the parameter y equals x plus b. I told you about L. My solution must be only on L. That's what I want the function to return. Part of the input is a set of half-planes. And I want a point that maximizes a cost function. Cost function parameter, just to keep it simple, but let us see that I and this point must be in the correct side of each one of the half-planes. Inside each one of the half-planes. So how can I solve it? Simple. And I can do it in linear time. What should I do? I'll look at the line L. I'll compute the intersection point. A notation that I'll use a lot today is every time that I'm writing L sub I, it's a line bounding the half plane edge I. So half planes are all the points on one side of the half plane, so part of my input is, of course, which side do I mean? So what am I doing? I partition the half planes into ones that look upward and ones that look downward. Looking upward meaning contains the points x equals 0 and y equals infinity. So if you believe in heaven and hell, then you can assign one side as, and the other point is way down below as 0 and minus infinity. So some half planes look upward, some half plane looks downward, and I'll assume that none of them is vertical, just general position as usual, right? Rotated by some random noise, so I don't have such half planes. What do I do next? I compute, what happened? I compute for every half plane that looks upward, I'll compute its intersection point, or the intersection point actually of the line that defines it, the point of intersection of H1 and P1. Meaning what? Where are the points which are both on L and on P1? These points, same for P2, same for P3, sorry, and the points that are relevant for me as a possible solution, remember I'm trying to satisfy all the constraints. Basically it's going to be I need to get enough vitamin A and enough vitamin B and enough vitamin C, and it needs to be the same diet that satisfies all of them. So I computed these points and think about the rightmost point out of all the points of the PIs. So if you think about it, P2 defines a ray on L that just go all the way to plus infinity, go all the way to the right. And that's for P2. P1 defines a similar ray. P3 defines a similar ray. But since I need to be in the intersection of all these rays, the ray that has the smallest intersection is the one that starts at the maximum, the rightmost, out of all the intersection points of what L and all the half planes that points upward. And I am going to do the very same thing with half planes that points downward. Compute their intersection points. It's essentially these intersections points are nothing but L, this one special line, the bold-faced line, intersected with Li for every I. These are the points, except that every point that I compute as L intersected with Li comes with a direction. The feasible region for such an intersection point is either to the left of Pi, because if it's pointing downward, or to the right of Pi, if it's pointing upward. And what do I do if, depending on my cost function? Well, I first check if along the line, all these rays, some the rays that shoot downward, some rays that shoot upward, all these rays have any point in common, which happens if and only if, how? I'll find the rightmost point out of the pointing upward. I'll find the lowermost point, or it's not necessarily the lowest, the leftmost point and the rightmost point, out of all the half planes that points downward. Again, look at the fur. This is a half plane that contains minus infinity. So ray that points to the right, that points to the left. And you can ask along these rays, think about them as open parentheses and close parentheses, either any point that lies in their intersection. There was a fair amount of hand wave, but does it make sense to everybody? Everybody understand how in linear time I can do it? Find the maximum, find the minimum, find the unique interval in the intersection, and now either return the maximum point or return the minimum point, depending on your cost function, the highest or the lowest. So it's linear time, and what's also important here, so it's between P max and P min, that is the maximum out of all the means and the minimum out of all the max, if you wish. But as you see, the 1DLP might happily also tells you, hey, there is nothing, no intersection of all these ways has absolutely no point in common. Quite possible, right? Here is L. Here is age 1. Here is actually, I don't like this example. L, age 1, age 2, and what will be my, what is a feasible region, feasible area along L are all the points that are on this way and at the same time on this way. And these ways have no point in common. So you're saying on L itself, there is no solution to my linear programming. Okay, so finding the maximum is linear time, just scan them. Minimum linear time, just scan them. And that's how you find if there is a solution, and if yes, then it's one of the endpoints of this interval. Okay, now let's describe the n-square algorithm for the linear programming. And I'll just remind you that we have already n log n algorithm for the linear programming because I had the half planes. I computed their intersection, computed all the vertices, computed the intersection is, say, via gram scan, or gram scan via duality, or divide and conquer, or you can even do gram scan in the primal and compute the lower envelope and upper envelope. So you have an n log n algorithm. Nevertheless, I'll bore you with n square time algorithm. So it's going to be an incremental algorithm. We saw already a few incremental algorithms. One was gram scan itself, add the points, but then the order of adding was from left to right for convex hull. One algorithm, just checking sound-wise. Still on. Okay. So we saw the Delanoy triangulation. We saw the trapezoidal building, finding yourself in a map. So it's not our first order. So I'm going to look at all the half planes. And I need to assume something about the cost function, the cost direction. Remember, it's linear. It's like the wind that pushes me in some direction. Unless I'm saying otherwise. I'll say my cost function, C, would be 0 and 1. And I'm trying to find for a point, the point P that is, let's go to this side, if these are my half planes, here are my half planes, and my cost function is what I wrote right there, C equals 0 and 1. That's my cost vector. That is, I'm trying to find P that minimize C times P, subject to P is in age I for every I. P is inside the feasible region, that is inside all the half planes. And at the same time, P is a point that minimizes this cost function, which is a fancy way to say inside the polygon find, help? Here is a region that is the intersection of all the edge I, and which point, familiar with this notation? Just like sigma, just with intersection. So H1 intersected H2, intersected H3, satisfies vitamin 1 and satisfied vitamin 2 satisfied. And so that's a region of the intersection. We talked about it last meeting. That's a feasible region. So every point here satisfies all these constraints, is inside all the edge I. And out of all the points, my solution to the linear programming problem is, help, which point? It's a vertex, which one? The lowest one in this case, right? This cost vector C that points over here. Well, if I maximize, C is pointing to this direction, so if I'm trying to maximize, it would be the highest most point. If I'm trying to minimize, it would be the lowermost point. But point with a maximum or minimum y. And of course, in this example, it's a vertex. And I can always assume that I rotate my coordinate system, or just the algorithm doesn't care to which direction C points to. But for the explanation, it will be easier to assume, look for the lowermost point. So that would be my cost function. My cost vector points downward, but it doesn't really matter. OK, so I start by inserting two half planes. And now I'm going to add half planes one by one. And as I mentioned, if I want to compute the feasible region and I need all the vertices, my algorithm will run in at least n log n. It's at least as hard as sorting. So I'm not going to do it. Even though I'm saying that it's n squared, what I'm going to do is to keep in hand the vertex that optimize my solution so far. I'll have the first two half planes, and then the first three half planes, H1, H2, H3. Then it will be H1, H2, H3, H4. And each moment, I will have the optimum vertex for what I have so far. And when I'm adding a half planes, maybe I need to update something. Maybe I don't need to do anything. In more details, edge I is a ith constraint, H1, H2, dot, 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 Hn. It's a half plane. Li, we had it, is a line that bounds Hi. Ci is a feasible region. It's H1 intersected with H2, intersected with all the half planes, but I stop at the ith one. I don't go all the way to n. I stop at the ith one. So I can speak about Ci. It doesn't mean that I keep all its vertices. I will have to work way too hard if I want to keep all its vertices. Still, it's clear what do I mean by points in the feasible in Ci. It's all the points in the plane that satisfy the first half plane, the second, the third, all the way to the ith one. What happened with the I plus 1? I don't care. It's in the future. Ci is a feasible region. Again, warning, I don't keep this guy explicitly, but I know that it exists. Vi is a vertex in the feasible region of the Ci, and that's where I obtain my optimum. So you see H1, you see H2. L1 is a line that bounds H1. L2, the line that bounds H2. My cost function points downward. So the feasible region is the intersection of these two half planes. And the lowermost point, which I'll call V1, is this point over here. Right? That's the optimum solution. Wait with this. This point is the optimum solution for the linear programming that involves only H1 and H2. What about H3, 4, 5? Way in the future. So let's play. H1, H2. Where is V1? Not too hard. That's V1. Where is the intersection? Right here. So that's C2, the intersection of H1, H2. And here is H3. And my question is, this is actually V2. I'm sorry. That's the optimum solution because I start from I equal 2. So H3 doesn't exist. That's the optimum solution, the lowermost point. That is both in H1 and in H2 at the same time. Where is V3? Yep.
Does V3 equal V2?
That's also V3. Everybody agrees? These half planes doesn't violate V2. V2 is inside H3. So if it was the optimum solution earlier, it's still the optimum solution. If that's the cheapest and this doesn't, then the new half plane will only make my solution possibly more expensive or at least not cheaper. It will be either the same price or even more expensive if I'm trying to reduce the price. So this is also, so V2 is also V3. Cool with everybody? What is C3 didn't change at all, right? It's still the intersection. Here is H4. Where is V4? Didn't change at all. C4 did change in this case. I did chop all the points in infinity, but again, I'm not interested in computing all the vertices. I'm only interested in knowing what's optimal. Okay, let's see some action. Age. Age 5, it never works. Age 5. Now I cannot hope that V4 will work for age 5. It's not well shown, but you see that it's outside. V4 is below the line of H5, below L5. So the new optimum solution is hard to see, but it will be right here. So this is V5. This new optimum solution that I'll find for all the points, including H5. So that's a case that V4 and V5 needs to be modified because this drawing is so small. Let's add another one. Here is age 6. And this would be V6, if you assume that this half plane is a bit going lower. If the half plane, by the way, is completely horizontal, then I can pick either of the two vertices, right? But I'll always pick a vertex, that we said. Remember, we had a theorem in the last meeting that said that no matter in which dimension I am, the optimum solution is obtained at a vertex. maybe not only at the vertex, but I can limit my search to vertices only. Yeah.
So when we insert a new line and we find that our optimal point needs updating, is it always the case that the new optimal point is going to be on the line that we just inserted? Or on
I will be more than happy to answer it very shortly. So just to understand, the picture here is H3, C3 is somewhere here, and V3, C3, V3 is the lowermost point inside C3. And once again, I'm not bothering computing C3. Actually, you already guessed what I should do instead. Okay, so here is the theorem, but the theorem is actually dictates the algorithm. So I had already, I larger than 2. I already computed the intersection of what is V2, the intersection of the first two half planes. Now, if Vi minus 1, V2 is inside H3, if it's not broken, don't change it. You're adding constraints, but whatever was your cheapest solution earlier will still say your cheapest solution because it doesn't violate, it's inside H3. It's whatever you had that satisfies H2, H1, and H2 is now also inside H3. So you don't change it. Vi is nothing but Vi minus 1. And in this case, the time that we spent so far for the algorithm to add Hi is just a constant time that took me to check that the previous solution, the Vi minus 1, is inside Hi. So in this case, I need to spend very little time just to validate that a point is inside a half plane, constant number of operations. The same goes in any fixed dimension. In D dimension, it takes ln D multiplication and summation to compute if a point is inside the half plane. Yeah.
How is like CI stored?
It's not.
It's not at all.
Not at all.
Do we need to like record like previous, like if we had like a case where it was like a half pin this and a half pin of, there's no points. Do we need to like to know about previous entries or?
No, I don't keep CI. I keep a vertex of VI because remember I want it to scale for higher dimension, and in higher dimension I can have exponentially many vertices. I only keep the optimum vertex that I had so far. So I can definitely speak about the feasible region, and in some of the homework question I just ask you to check if the feasible region is empty or not, but I don't need to know who are all the vertices or faces or edges of the feasible region. Okay, what happens if H3 does not agree with V2? Vi minus 1 is not in Hi. Then we will have a theorem, thank you, we will have a theorem that says you need to find the new Vi. But your new Vi is, well, it's somewhere in the 2D, so maybe it looks like a two-dimensional place. Like minus 1 doesn't, but it does tell me that if in this case, not that it's inside. And I need to first have this check. Notice, I placed H3, here was V2. V2 was not on the line that bound H3. But on the other hand, H3 did not violate V2. When I inserted H6, the blue guy, H6, the new optimum, it did violate V5, V6, there was violation, but in return, the new optimum solution was on the line bounding H6 as well. Yeah?
Does that mean like you store the line so that like if Vi minus 1 is not in H, then you like
Yes, yeah, exactly. So the first case is trivial. If it's not broken, if vi minus 1, the optimum for the first I minus 1, is inside the ith one as well, then it's the same optimum solution. Why? No reasons to make it more expensive. And if it worked for the first two vitamins and it also worked for the third one, then that's still the cheapest diet. Let's prove the second one, because the second part, that if vi minus 1 is not in hi, then it must lie on the line Li itself. And here we are going to use the cat analogies from last meeting. So here is vi minus 1. Optimum solution inside ci minus 1, say the lowermost point. Here is hi in brownish, the line Li that bounds hi, and vi minus 1 violates hi. Now, where is vi? It should stay in hi, because it should satisfy it, and at the same time, it should be also inside ci minus 1, the intersection of all the previous constraints, because it needs to satisfy all of them. But assume by contradiction, it's not on the line Li itself. The half planes hi, it is inside ci minus 1, but it's not on the line itself. What do we know? Which is cheaper, vi or vi minus 1? Which is lower, obviously. Vi minus 1 in the picture, and also because it should we are trying to minimize the cost, and it satisfies fewer constraints, so it's probably cheaper. Vi, therefore, is more expensive. Vi that is not on the line. What do I know about this segment? Ci minus 1, intersection of half planes, it's convex. Each half plane is convex, intersection of convex is convex. So this segment, this point is inside ci minus 1, this point is inside ci minus 1, the whole segment is inside ci minus 1. This point is inside hi, this point is outside hi, therefore, walking along this segment, there is a point at which I exit hi. What do we know about the cost function? Where do I use that the cost function is not, say, a quadratic part that has some minima at some point, and if I'm to the left of the minima, I'm too expensive, but then if I'm to the right of the minima, I'm also too expensive. It's a linear cost function, meaning that, according to our cat claim, if moving a bit distance help a bit, then keep walking in the same distance, it will keep getting better and better. You will not reach some local maxima, and then it will start grow up again. So as I'm walking, the cost here is more expensive than the cost here, meaning walk linearly along the segment, and your cost becoming cheaper and cheaper. At some point, Q, I'm exiting hi. My cost at Q is better, is cheaper than my cost at Vi. Therefore, I would pick Q as the optimum solution, or at least it at least proves that Vi that just floats inside hi is not the optimum solution, because I just showed you a point that is better than it. So it's contradiction. Contradiction to what? That Vi is not on the line Li itself. Fair with everybody? So you're adding a half plane. If there is no violation, don't do anything. If there is a violation, then now you're solving a new linear programming problem, but it's linear programming problem in one-dimensional less. Instead of two-dimensional linear programming, you now have a one-dimensional linear programming. Just look for a solution on the line that bounds hi itself. Okay, so yeah, everybody buys this proof? Everybody understand what I'm trying to say? Either no violation, or if there is violation, solve the one-dimensional LP. So here is a new algorithm. Compute C2, which is age 1 and age 2, and compute V2, just the first two half-planes. That's just the starting of the algorithm. For I goes from 1 to n, I'm adding the half-planes age I. So it's incremental, assuming that I'm solving all the half-planes 1, 2, 3, all the way up to I. If vi minus 1 is inside age I, then do nothing. Just relabel it as vi instead of vi minus 1. Not broken, don't fix it. Else, vi must be on the line li, so let's reinterpret the parameters here. I'm calling the 1D LP, and my solution is with all the half planes, h1 dot 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 hi minus 1, all the half planes that I have until the ith stage. And instead of giving you the half planes hi, I'm telling you only look for a solution on the line that bounds hi, only on li, the line that bounds hi. And that's what the 1D LP would return to me if a solution exists at all. But if the 1D LP does not have a solution on this line itself, then there is no solution at all. Because our proof says if there is a solution, it must be on the line. And when I look at the intersection, this linear algorithm on this line, there was empty. So at this point, there is no point of adding more half-planes. Just the feasible region is empty, and if you add more half-planes, it will only become more empty. Else, you did the 1D LP did return a solution, then vi is a solution of this 1D LP, and continue until you're done. How much time does it take? The 1D LP takes linear time. 1D LP. Take linear in I, linear in how many half planes do you have. So what was the time altogether? Well, we saw this sum multiple times, 1 plus 2 plus 3 plus 4 plus dot 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 n, which is theta of n squared, right? It's n plus 1 divided by 2, so no more than n squared, no less than n squared, up to constants. Okay, so that was a great, what would be the unimprovement, the opposite. We had n log n, and now we finally have an n squared time algorithm. So not great so far. And it's n squared, and it could be, now, am I sure that it's n squared always? Not really, because let's play with this. What will my algorithm do in this case? So I have h1 and h2. So v2 will be right here. That will be v2. I'm inserting h3. So v3 is here. And now I'm inserting h4, and h4 said v3 doesn't violate me. So that's also v4. So that's also v4, and I'm inserting h5, and I'm inserting h6, and none of them violate by h3. So in this case, the algorithm runs in linear time, just constant per h1. So when will it be, when will I get this summation? If, yeah. Exactly. If now I'll insert them starting from, this is h3, this is h4, h5, h6, So now I'm going reverse order. And now every half plane that I'm getting involves calling the 1DLP, where the input to the 1DLP are everything that I had so far. So it's I minus 1 half planes. So it's all about the order of the insertion. It's the case that one order creates it to be in linear time, another order creates it in linear versus n squared. And in the homework, I ask you to show that in 3D it can be n cubed for the very same reasons, with bad order. What is the correct order? I have no clue, because it's chicken and the egg. I need to know the solution. So what do? I insert the half planes at a random order. Take a random permutation, what we did with Delanoy, what we did with the trapezoidal map. Create a random permutation of the half planes, and now insert them. That is, I'm not assuming that the input is nice in any way. The input is half planes, and they can be good or bad, or I have no clue. I'm taking matter to my hand by creating my random permutation. And I want to convince you that the expected running time will be linear. No matter what the input is, the expected running time will be linear. No matter what the input, provided expected on what? If I don't change the input, then when I'm saying expected, it's on what? It's you are generating all permutations of the half planes, all the order of inserting the half planes. Each time, once the order is fixed, check out what's the running time of the algorithm. Some running time for some orders, it will be very slow. Some other order of the same half planes will be very fast. Sum up the running time of all your experiments, they're all different orders, and divide by the number of permutations, all the n factorial permutation. That's the average running time when you take the order at random. So that's the meaning of expectation here. And it sounds like a very unpleasant combinatorial problem, but you'll see that it's very simple. Why would it be so simple? Because the running times that I'm trying to get will be summation of something that each one is very simple. So let's assume that input is general position. So I don't have three of these half planes whose bounding lines intersect at a point. Again, I don't have three half planes with a point shared to the three lines that bound them. Of course, three half planes might intersect, but not the lines that bound them. I don't have a point that lies on three bounding lines. It's actually, I'm asking you in the homework to show that if this is not true for your algorithm, then it's actually faster to the algorithm. It's just improved. But let's not worry about it. So assume that I inserted all the half planes already. Let's say up to the ith half planes. Remember, I'm living in the 2-dimension general position, and I'll assume general position, the optimum is unique, so not on an edge. It's the optimum, not an edge that is equally good. The optimum is unique, just a point. How many half planes are involved in determining this point? How many half planes are involved in determining the vertex? Here is the intersection. The moment that I told you what's a cost function, you're saying, say, the cost function points downward. Here is a vertex that is the optimum solution. I inserted I half planes until this point, but the optimum is determined by this half planes, h double prime, and this half planes, h prime. And my question for you is, what is the probability that vi minus 1, the optimum that I have until this moment, without the hi, what is the probability that vi minus 1 is different than vi? It's random event, right? Depending on the order, and the order is some random thing. So depending on the order, the solution that I had until now, solution that I have right here, it could happen, it can not happen. So think about it this way. I have an array with I balls, and out of all these balls, they are almost all of the same color, except that 2 of them are red. I have exactly 2 red balls. And what are these red balls? One of them will be relevant to H prime. One is relevant to H double prime. But I'll just think about them as special half-planes. Out of all the I half-planes, there is something magical about these 2. And I don't care at all what is this properties that makes them special. But they are uniquely defined. Out of all the I, there are exactly 2. And now I scrambled all the balls, create a random permutation, and I take the rightmost one, and I ask, what is the probability that the rightmost one is red? It's not hard. Each one, since it's random permutation, each one of these balls has the same probability to be the rightmost one. What is the probability that H double prime ended up to be the rightmost one? And I'll tell you in a second why I'm obsessed about the rightmost one. Probability that this particular ball is the rightmost one. This ball can end here or here or here or here in each one of the places. And because it's random permutation, each location of the H double prime is equally likely. So the chance that it will end in the rightmost one is 1 over I. Probability is this one, and right here is 1 over I. Probability that one of them added in the rightmost place is 2 over I. That is. Now, let's think about the problem. What happens if I start the insertion process by first inserting H double primes, then inserting H primes, that's H1 and H2, and then I insert all the other half-planes? Then no violation ever happens, right? H prime, H double prime, I inserted them, computed V2, and never needs to change it. So, or let's play it the opposite direction, and that's why it's called backward analysis. So one of these half-planes, all these I half-planes, one of them was added in the ith stage, but each one of the I half-planes has exactly the same probability to be inserted in the ith place. Why do I call it random, backward analysis? Not I call it. Why the name is backward analysis is, let's assume that I put all the half-planes already here, computed the minimum, and now I remove one of them at random. I'm playing the movie backward. So when I inserted them, I went to left to right, that's insert, and now I delete, playing the movie in reverse, and asking pick a random permutation, meaning that I can pick each one of them to be removed. What's the probability that the one that I removed now is one of the 2 special ones? 2 over I. So the probability that my old, if Vi minus 1 is different than Vi, then it happens only if the ith half-plane that I added is either this one or this one. If this one and this one are not the last half-plane, the ith half-plane that I added, then the previous, like if these are the 2 reds, then the moment that at this point in time, in I minus 2, both of them are already in, that's the term in the optimum, and then when I'm adding the rest, nothing changes. So Vi minus 1 and Vi will be the same point, the same optimum. Only if the red is the last one that I inserted, this red or this red, only then Vi minus 1 and Vi will be different. What's the chance that it happens? 2 over I. Why am I excited about? See in a moment. Okay? Everybody agrees? Where does it stand in the overall analysis? Wait for me, but at least you see if I added I of them, pick one at random and remove it, but each one has the same probability, what's the chance that you change the optimum? 2 over I. Agree? And again, the random permutation just implies each one of the half planes has the same chance to be the last one that is added at each step of the algorithm, of course. So, and again, where did the 2 comes from? Because the VI is determined by 2 half planes equally helping. In 3 dimensions, of course, it would be half spaces, and then it would be 3 over I. So what is the probability that one of them is HI? We had it, 2 over I. If yi is a random variable, a flag, don't get confused, the flag is on only if vi minus 1 and vi, the optimum has changed. I needed to update it. What is, therefore, the probability that hi is one of the other half planes, not one of the 2? Well, if the probability is that it's that they are more that I needed to update the opt was 2 over I, then 1 minus this probability is I minus 2 over I. So random that's a very large number. That's almost 1. And if this happens, then as we'll see, I need to place very little work, right? I just need to validate when I'm inserting one of the other ones that it doesn't violate my opt and move on, move to the I plus 1. And that happens almost always with this probability of I minus 2 over I. It's almost 1. Formally, if yi, now assuming that I fix the permutation. Permutation is fixed. Yi set yi is a flag, yi is 1 if vi minus 1 is different than vi, I updated vi, and otherwise yi is 0. What will be my overall work in this case? My overall work would be a constant that I don't show here, times, when I'm sigma from 1 to n, of, I need to spend a constant at each step, plus, if you needed to update the optimum, then you are calling the 1D linear programming, which takes how much time? I, linear in I, times yi. Right? If yi is 0, then I times yi is 0. I didn't always spend is a constant just to validate that the optimum is not broken. If yi is 1, then I'm spending I, linear constant, times I, times the 1 that comes from having it there. This is the overall running time of the algorithm once the permutation is fixed. What do I want to know? I want to know what is the expected running time out of all the permutations, E of summation, and every time that we see E of summation of stuff, we immediately, uncontrollably put the E, remember, E of x plus y is E of x plus E of y. What do I reveal? E of the summation is sum up all the ones here, and guys over here, so this gives you the n, plus I, constant, the 3 over here, goes outside the expected. What is the expected value of yi? It's just the probability that yi equal 1, that is that I have a violation, which is 2 over I. Summation of, at each step, sorry, I'm missing the sigma sign, it's n plus the summation of, look how cool it is, 2 times 2 divided by I times I cancel the I, so sigma of 2 divided by I times I, give me 3n. Or put it in other words, what is the expected work at the I step? Meditate only on the I step. What is the expected work? It's a ith step, I'm spending a constant plus I work if I need to call the 1DLP, but I need to call the 1DLP only in 2 over I of the cases. So the expected work at the ith step is 1 plus 2 per step. And where did I use the linearity of expectation? Instead of thinking about some events depends on each other, I broke it into one half plane that I'm adding at each point and asking what the probability is that a violation happens. And it's nice. Think about it. The larger I is, the more time I need to spend for the 1DLP if I call the 1DLP. Larger I is, the 1DLP takes more time, but on the other hand, the probability is almost surely that I don't need to, and I just can add these half planes at random. So, as I said, it was quite an achievement where people realized that previous algorithms that were significantly more complicated are not needed, and such a simple argument gives you a linear time algorithm so nicely. Okay, and we didn't get to the 3DLP, but that's fine. But you need it for the homework. So 30 seconds more because you need it for the homework. Let me just 1DLP. What do I do? I have the half planes in 3 dimensions. I insert the half spaces in 3 dimensions. I inserted them at random order, again, picking a random permutation. Vi minus 1 is the optimum solution. I pick 3, compute V3, intersection of 3. Now I'm in the case of I equal 4. If Vi minus 1 is inside Hi, now it's half spaces, but it's still the same check. Don't do anything, just called it Vi. Else, if Vi minus 1 is not in Hi is a half space now, then the same argument now tells me that the new Vi is not floating in this half space in the free world. It is on the plane. Now Li is not a line, it's a plane that bounds the half space. So it's now becoming just not 3-dimensional problem, avocado, oranges, bananas. It's not becoming 3-dimensional problem, but it's 2-dimensional problem. And Vi is on the intersection of each half space with the plane that bounds Hi. So now it's 2-dimensional problem, which I solve how? Recursively by calling the 1DLP and so on. So it's the same problem, and the running time is therefore yada, yada, yada. Running time will be in D dimension. There is an unpleasant constant, curse of dimensionality, the D factorial here, when you're going up the dimension. But as far as dependency on N, very cool. It's linear time, expected linear time, no matter. And it's nice because the worst case does grow exponentially. The worst case, bad permutation will be N to the D. Expected case is only order N, I think. Yeah. Thank you.